In this video, we explore the concept of linearity. In the previous video, I decided to implicitly assume its definition by writing the form of a ordinary differential equation, and assuming that you, the audience, know what linearity means. But here I'm going to explicitly state what makes an ordinary differential equation linear. So let's dive right into it. Linearity depends on three conditions, the first of which is the dependent variable and all of its derivatives must have exponents of 1. And what does that mean? It means the dependent variable and its derivatives should appear like this, but not like this. Not in a case where they have an exponent of 2, exponent of 3, or any other exponent. For example, look at this case. This is an exponent of -1, but not an exponent of 1. 1 is not the same as -1, etc. The second condition for an ODE to be linear is there must not be a term involving the product of the dependent variable and any of its derivatives. So, for example, you should not have the first derivative multiplied by the dependent variable itself, and you should not also have the second derivative, as well as even the derivatives themselves multiplying each other. And if you do this, you violate one part of the rules in this. If you have a product of the dependent variable and its derivatives, or the derivatives with themselves, you will end up having an exponent of -1 for the dependent or the independent variable. Here's what I mean by that. Let me explain that briefly. You have, let's say, y prime times y itself equal to x. Let's say you have this as the differential equation, and you decide that you are going to make the derivative the subject. You would have y prime is equal to x over y. And in this case, you now have a y raised to the power -1, which violates the rule we stated here. So that is how to link it. You can even absolve condition number 2 into condition number 1 as 1. Condition number 2 also has a subtle implication that the coefficients of all of the y primes, the y's, the y prime primes, as in the derivatives of the dependent variable and the dependent variable itself, should be functions of x. Okay, none of them should include the dependent variable or its derivative. So you can't have p of y. You can have p of x, y. You can have q of x, and so on, but you can't have p of x, y, p of y, y, or p of y, y prime. So that's another way you can think about it. For example, instead of having x plus 1 multiplied by y, you ended up having x plus y multiplied by let's say y prime. In this case, you just found out that if you multiply this out, you would have a product of the dependent and the independent. So if you take this as p of x comma y, it violates the rule. Like, it's multiplying one of the dependent variables or its derivative by a function of y, a function that involves y, which is a violation. So those are the two side implications of the second condition. The first implication is that it simplifies back to the first case if you divide both sides by one of the multiplicants. If the product is y prime prime, and you divide through by, let's say, y prime, you would end up having an exponent either than 1 for y prime, which is a violation of this. And the other implication is that if you have a product of p of x, y, and a function, the function itself or its derivatives, it also violates the rule, because in the end you would have a product of the dependent variable and its derivative, or the dependent variable and itself. So that's it. Okay, so the next condition is the dependent variable and any of its derivatives must not be an argument of a transcendental function. Okay, what's a transcendental function? A transcendental function is a function that cannot be expressed in terms of ordinary operations like plus, minus, multiplication, and division. So if you take this one, for example, there is no way you can finitely find an expression for sine of y in terms of the basic operations we know. So mathematicians call them transcendental functions. So the examples of those functions that behave this way are the natural log function, or any log function in general, the exponential function, the hyperbolic sines, or the hyperbolic trigonometric functions, and the normal trig functions as well. And that takes care of transcendental. Well, now what's an argument? An argument is the parameter you put into a function to get the value you want, the independent variable of a function. But in this case, we want the independent variable of such a function to always be the independent variable of the equation, like x or t, but not the dependent variable like v or y or x. So in this case, something like this, y prime is equal to sine of y, is not a linear differential equation. And the reason is simple, that we have a transcendental function being a function of the dependent variable. So this is disqualified, sine y, disqualified. And there are other examples you could look for. And this is the order I recommend. First, look for red flags that will nullify or that will break the rules in condition 1. And then go to condition 2, look for red flags that will nullify rules in condition 2. And then you look for red flags that will nullify rules or that will break the rules in condition 3 as well. So if you do this in this order and you make sure you do it all the time, you will not miss it. If you see any transcendental function, check whether it contains a dependent variable inside of it. After that, you go ahead to check whether there are other exponents apart from 1 for the dependent variables, and check whether there is a product of dependent variable and its derivatives. So that's all you need in order to check for linearity. Let's take some few examples. Example 1 says y is equal to sine of x, y prime. Let's check whether there are exponents of y and y prime that are not 1. There is nothing like that. Y has an exponent of 1 and y prime also has an exponent of 1, so we are safe. Now condition 2, we don't see anywhere that whether y and y prime are a product. There is nowhere y is multiplying by y prime, so we are safe for condition 2. Now condition 3 says we shouldn't have y inside of a transcendental function. Even though there is a transcendental function, y is not an argument of the transcendental function. It is x that is. So this is linear. The next one says square root of y is equal to y prime x plus 5. Is this linear or not? Well, let's check. Does y have an exponent other than 1? Yes, y has an exponent other than 1. Now, is there a way to manipulate this into a different form that makes y not have that? Let's check. If you square both sides, we would end up having y prime x plus 5 raised to the power 2. But in this case, we ended up having y prime squared, okay? In an attempt to take away the half power of y, we introduced a square on the y prime, which makes this inherently not linear. This is not linear because it failed condition 1 brutally. So not linear. Okay, let's check this one. Is this linear or not? Again, the same trick. Sometimes the equation can be written to look like it is non-linear, but it's still linear. So let's check for that. First of all, we see that this has a power that is not 1, and we are trying to see whether there is a way we can take it out, okay? If you square both sides, we'll end up having y prime is equal to x plus 2y raised to the power 1. So in this case, we have a y prime to the power 1 after we apply the square, y prime to the power 1 equal to x plus 2y, just 2y. So this is linear, but it looked non-linear. If we had concluded early by just stating that we saw an exponent of half, so it can no more be linear, we would have missed the point. So this is linear. So this one says y prime over y is equal to sine of x plus cosine of x. Let's check whether this is, like, first of all, y has an exponent of, y prime has an exponent of 1, y has an exponent of -1. But is there a way to transform this to be in the normal standard order? Y prime is equal to, this is just a function of x, so I will call it a function of it. Let me just say q of x, y. This is linear because this has an exponent of 1, this has an exponent of 1. We don't have y inside of a transcendental function, even though there are transcendental functions. So this is linear. Next, is this linear or not? E to the power v equal to tv to the tv prime plus 5 cos t. This is not linear. I'm going to tell you straight away because I saw this. So whenever you see the dependent variable, which in this case is v, in a transcendental function, just conclude. All the others don't have red flags. It's only this one that is a red flag. When you see an obvious red flag, conclude straight away. When you don't, continue checking for linearity. Not linear. Here, is there a red flag? Our dependent variable is psi. So is psi having an exponent other than 1? Yes. So we conclude straight away. This is not linear. Okay, this is another one. The dependent variable, always focus on the dependent variables, not the independent variable. They don't contribute anything. The dependent variable here is phi, and phi has a derivative, and that derivative has an exponent of 1. Phi itself also has an exponent of 1 in the whole equation. So we conclude that it is linear. But let's check further. This is the independent variable, so we ignore it. This is the independent variable, so we ignore it. This is a constant, omega, so we ignore it. This is the independent variable, so we still ignore it because we would have said it has an exponent of -1, but it doesn't count. So this is linear. Here we have y prime sine x plus ln x y plus w of x. You can interpret w of x anyhow you want it, but you can interpret it as a generic function of x, or you can interpret it as the Lambert W function of x. So you can interpret it any way you want, but it's just a dummy. I'm trying to say that x doesn't matter. It doesn't matter what function x finds itself in. If x finds itself in a bizarre function like e raised to the power tangent of tan inverse of sine inverse of, it doesn't matter. Don't worry about the independent variable. Only worry about the dependent variable. So here we have an exponent of 1 for the derivative, and we have an exponent of 1 for the function itself. So we conclude that it is linear because there are no transcendental functions with the function in it, and there are no products of the derivatives and the function itself. Again, we have this one. Is this linear? Well, we have a function. I mean, let's check for condition 1. We have the function raised to the power 1. We have the derivative raised to the power 1. So we conclude that it is linear. But wait, look at the coefficient functions. The coefficient functions, as we already established, must not have a y in them. I didn't state the forms of p of x and t of xy, but you should immediately flag it as the fact that this one is a function of t of xy. Like it is configured to contain a y in it. Even if it doesn't contain a y in it, you need to look at the generality of it. The general case is that this function might have an x in it, a y in it. And if it ends up having a y in it, and this thing goes to multiply by that y, it will have a product of y and y prime, which is a violation of condition 2. So this is not linear unless otherwise stated that t of xy somehow depends on x only. Right, good. So this is not linear. Not linear. At least not in the, on a first glance, this is not linear. This is not linear because of this t of xy function over here. Well, there is this principle in physics called superposition. The principle of superposition depends on the fact that the wave function is linear. Well, if the wave function psi is linear and you find solutions for it, or let's say you solve a differential equation, you finish. We haven't actually started solving differential equations, but if we do, and we happen to find solutions for it, and one is of the form c1 e to the power 3x or something, and another is of the form c2 e to the power 4x or something. Okay, if we happen to find solutions like this for the functions, the superposition principle states that the sum of the solutions to the functions is also a solution. The sum is also a solution. So y equal to y1, psi equal to psi1 plus psi2 is also a solution to the differential equation that was solved to get both y1 and y2. And that principle of superposition is possible only for linear differential equations, not nonlinear. If it is nonlinear, then the principle of superposition doesn't apply. Yeah. So for completeness, I would rewrite this as c1 e to the power 3x plus c2 e to the power 4x. And this is also a solution. If this and this are a solution to a particular differential equation, that same particular differential equation has a solution this. And so that is it for this video. And this is just an importance of linearity in differential equations. And differential equations is kind of the language in which physics is written, so you should take note of this. So thank you very much for watching, and I'll see you in the next video.